Let's understand a little bit more about electrode potentials. And simply, electrode potentials are measures of the amount that a half cell, wants to either gain or lose electrons, measured in volts. So if let's say we've got a metal in one of the half cell, and if it wants to lose electrons a lot, it's going to have a negative electrode potential. And if it wants to gain electrodes a lot, it's going to have a positive electrode potential. And the scale of that negative and positive gives you an idea of the scale by which they want to gain or lose their electrons. So let's go back to our zinc-copper pair of half cells, and we're going to write a little table out. So we're going to have zinc 2+ ions, and they're in solution, and you've got zinc solid as the electrode, and we've also got copper 2+ ions, and we write the reactions like this in the reduction direction usually. So at the zinc electrode, we've got this reaction going on. We've got the zinc 2+ ions, and they're accepting 2 electrons and making zinc solid. Or the reverse. We'll say a bit more about whether it's the reverse reaction or this forward reaction, but at the zinc half cell that we saw before, it was actually zinc solid giving up 2 electrons and forming zinc ions, as in the backward reaction as written here. But the standard format is to write it as the reduction reaction, as the forward reaction. So the reduction reaction for the copper electrode is written like this. You've also got copper 2+ ions in solution. Let's not forget our little aqueous for the zinc as well. They also accept 2 electrons in the reduction direction, and they form copper solid. Okay, so what we can now consider is the electrode potential. I'll write a little column heading here for the electrode potential. So experimentally, these reactions have been measured with a voltmeter, and when zinc has been measured, we get an electrode potential of minus 0.76 volts. And when copper is measured, we get positive 0.34 volts. And the negative and positive we're going to deal with in a future slide, but basically you've got to compare it to something, and actually we compare it to hydrogen, and that's where the negative and positive comes from. We'll deal with that some more in a couple of slides time, but for now suffice to say that the negative and the positive give you an indication of which reaction is happening in each half cell. Is it the oxidation reaction or the reduction reaction? So let's write down a couple of rules. It's really the same rule written in opposite directions. So the rule is this. So the more negative, I'll write it in shorthand, the more negative electrode potential is the oxidation reaction. Okay, and the other rule is, the least negative electrode potential is the reduction reaction. When we say the oxidation reaction, the reduction reaction. You remember that in one half cell we've got oxidation going on, in the other half cell we've got reduction going on. Okay, so from these two rules we can work out which is which for the zinc copper. So we look at rule number one. The more negative electrode potential is the zinc, and so that's the oxidation reaction, and oxidation is in this direction. So in the zinc half cell, that is the reaction that is going to happen. Zinc solid is going to go to zinc ions in solution. And if we look then at rule number two, the least negative electrode potential, so this is actually positive, so that's less negative than a negative number. The least negative electrode potential is the reduction reaction. And so this is the reduction reaction for copper in this direction. So you're going to have copper ions in solution, accepting electrons from the electrode and forming copper solid around the electrode. And that's what we saw when we studied it. And so there we have a quick rule to allow you to find out which reaction, oxidation or reduction, is happening in each of the half cells of an electrochemical cell. Okay, let's have a look to see how we can draw electrochemical cells. And when we say drawing electrochemical cells, what we don't mean is drawing a diagram. We just mean the shorthand drawing of electrochemical cells. And so let's have a look at an example to illustrate it. You just take the oxidized and reduced species from each of the half cells. In our case, the half cells are zinc and copper again, and we just arrange them in a row. So I'm going to draw it out now, and then I'll explain it later. So we're going to take zinc, and we'll have it as a solid. We'll have a vertical line, and then we're going to have zinc 2+ ions, and they're in solution. And then we'll have a pair of double lines, and then we've got copper 2+ ions in solution. We'll have a vertical line and our copper solid. Okay, so let's explain what each of these elements means. First thing to say is that this is a half cell, and this is a half cell. So if you just allow me to summarize, to use HC as half cell. So this is half cell 1 and this is half cell 2. And then what we have to do, there's a bunch of rules that we need to follow. And the first rule is that the reduced species go on the left, at the edge of the cell diagram, that is. So the reduced species go on the edge of the diagram. That's our first rule. And then the oxidized species go in the middle. Okay, so in zinc's case, the oxidized species is the zinc ions, and they go into the middle, which is nearby the double vertical lines, and the reduced species of the zinc half cell is the zinc solid, and so they go onto the left hand side. Now, in the copper case, in half cell number 2, the reduced species is the copper solid, and so that goes on the outside, and the oxidized species is the copper 2+ ions, and they go in the middle. So that's why we write it in this order: zinc solid, and then comes the zinc ions, and then after the double vertical lines, we've got the copper 2+ ions followed by the copper solid. That's the order in which we write them, that we've just illustrated with these two blue rules. Okay, so I'm going to switch to green because then we're going to talk about these double lines here. And so they show the salt bridge. If you remember, in our zinc copper cell, we had filter paper soaked in potassium nitrate, and that was our salt bridge. That, if you remember, it keeps the charges neutral in each half cell. Okay, so then I'm going to switch color again to, I don't know, this color, purple, so that we can talk about this vertical line here. And the vertical line tells us that we've got different phases here. So we're separating different phases. So if you notice, we've got aqueous on one side and solid on the other side. And if that is just the case, then we draw a solid line, and if that wasn't the case, we would draw a dotted line. Okay, so solid line means different phases. Sorry, let me just correct a mistake I've noticed that I've made there. It's if they're in the same phase, it's not a dotted line, it's actually a comma. So let me draw a large comma here instead. Okay, so it's a comma for same phase. So if you remember when we had the Fe2+ and the Fe3+, that would be separated by a comma and not a vertical line. So lastly, notice that we've written zinc as half cell 1 and copper as half cell 2. Why did we do it that way? We could have easily just written it the other way around. We could still have the reduced species going on the edge and the oxidized species going in the middle, just written the other way around. So here's the other rule that we need to remember, and that is you're using the electrode potentials to work out which goes on the left and which goes on the right. And so the rule is that the one with a more negative electrode potential, so the half cell, let's write it like this, the half cell with the more negative electrode potential goes on the left. And another way of looking at that is that oxidation goes on the left. And that's the standard that we use, so that when we see a half cell written in this way, we can work out what's going on in each half cell. So the best way for us to embed this is to look at an example, so let's do that on the next slide.